Hello everyone, welcome to A plus BI. This channel is all about complex numbers, and in this video we're going to be solving an interesting trigonometric equation with complex numbers. How exciting this can get, right? So we have cosine of z equals a complex number, which is 3 over 4 plus I over 4. How can we find the z value from here? Okay, the cheap solution, let me tell you about that first, is basically you can arc cosine both sides, which is the inverse function for cosine. I know in the US they write it as cosine to the power -1, which is kind of weird, but a lot of countries use a different notation, which is arc cosine. So when you arc cosine of something, you end up with something like z. And on the right hand side, you're going to have something like arc cosine of 3 over 4 plus I over 4. But this is kind of meaningless, right? What is that supposed to mean? Can you explicitly express that? Probably not. Because there's no way to arc cosine any complex number, right? Unless you know the formula. Of course, you're not going to know that, would you? So here's what we're going to do instead. Instead of trying to arc cosine our way out of this, we're going to go ahead and use a formula. But what is the formula and where does that come from? That's what we're going to talk about first, okay? By the way, this problem is about complex numbers. This channel is about complex numbers. If you're new to complex numbers, go ahead and check out my lecture videos where I go over basics like polar form, Euler's formula, so on and so forth. If you like algebra, number theory, and trigonometry problems and a tiny bit of geometry, you can also check out Cyber Math, my other channel, my very first channel. That's Cyber with an S. Great, so let's see how we can solve a problem like this. We're going to start with a well-known identity, but we take things for granted, right? It's an amazing, unbelievable identity. Of course, it was discovered by Euler because he's awesome. So here's how it goes. Euler discovered that e to the power iz can be written as cosine of z plus I times sine of z. By the way, this also gives you the most beautiful equation. How? You can replace z with pi, and then on the right-hand side, you're going to get -1, which is amazing because you're kind of putting together the transcendental numbers with imaginary numbers, with integers, all in one equation. That's why it's called the most beautiful equation in math. Okay? But this is not the end of it, because what we're looking for is a formula for cosine, right? Yes, a part of this equation is cosine, but how do you isolate cosine from it? Are you going to be writing, okay, cosine z is equal to e to the iz minus I sine z? Even though this is true, it's not going to help you, right? So we're kind of going around the circles. Why is that not going to help you? Because you don't know what sine z is. Wait a minute. Can we not find sine z by using the Pythagorean identity? Yeah, we could do that. Maybe we're onto something. Let's check it out. We know that sine squared z plus cosine squared z is equal to 1. So if cosine z is equal to this, we can plug it in, right? So let's go ahead and substitute, 3 over 4 plus I over 4. By the way, we can write this as 3 plus I over 4. I got this problem from a book. I forgot the name of it, but I think it was something like an introduction to complex analysis or something like that. But anyways, these problems are very typical. But what am I trying to do? This is cosine z. I need to square this and find sine squared from here. Let's go ahead and find it. And again, I went over these in my lecture videos. And if you have any questions, feel free to ask. To square this sum, we're going to square each term like 9 and I squared. And then plus 2ab is going to give us 6i. That's going to divide by 16. One thing that I forgot to say, which is super important, and I almost always forget to say that, is that I squared is equal to -1. Because I is considered the square root of -1. There are actually two square roots, but one of them is considered the principal square root, which is I in this case. Okay? Now, how do you simplify this then? If I squared is -1, this is going to be sine squared of z plus 9 minus 1, which is 8, plus 6i divided by 16 equals 1. Let's go ahead and simplify this a tiny bit. This will become, actually we can first subtract it and then simplify it. And if you divide everything by 2, you get 4 plus 3i here and 8 here. And then once you subtract, you're going to get 8 minus 4, which is 4, minus 3i over 8. So cosine z is 3 plus I over 4, and this is sine squared. By the way, we have to square root both sides, right? And to do that, I'm actually going to do the following. Double the numerator and the denominator. You know what? Because that's going to help us. It's going to be easier to do. Now, I need to square root this, so I do need the square root of this number and the square root of 16, which is 4. Now, to find the square root, obviously there are two numbers, but let's go ahead and just stick to one of them for now. I can write this as 9 minus 6i minus 1. And then guess what that's going to turn into? This is going to be 3i squared, and this is going to be, no, not 3i squared, sorry about that. This is going to be 3 squared minus 2 times 3 times I, and this will be I squared. Guess what? That's equal to 3 minus I squared. With the square root plus minus sign, sine z is going to be plus minus 3 minus I over 4. That's the result. Okay, great. Now we have that and we have this. Can we use our formula to solve the problem? So what are we solving for, right? So let's go ahead and write this down here as well. Cosine z, remember our identity, the value of cosine z is 3 plus I over 4. And then we know that cosine z can be written as such. Let's see if that's going to help us at all. Cosine z is equal to e to the iz minus I sine z. So since you know sine z, you can go ahead and plug it in, but that's going to give you e to the power iz. Is that a good thing? Well, let's do this. Since we have sine and cosine, let's isolate this again and write it as cosine z plus I sine z. And then from here we can do the following. Replace cosine z with 3 plus I over 4. And then for sine z, we're going to have two options, but let's just use the one with the plus sign first. Plus I times 3 minus, wait a minute. Which one has the plus sign? Okay, 3 minus I over 4. There's always a minus sign here. And then let's see what this turns into. Since we have a common denominator, we can write this as 3 plus I plus 3i minus I squared, which is plus 1 divided by 4. This is actually 4 plus 4i divided by 4, which is 1 plus I. Aha, I think we're onto something, aren't we? Now, if e to the iz is equal to 1 plus I, how can I solve for z from here? Well, you can use the natural log or just think about the polar form. Again, these are all in the lecture videos, but if you wanted to turn this number into a polar form, this is what you should be doing. First, plot the number. This is basically the same thing as the vector 1, 1, right? Like a point on the coordinate system, but we just make it fancy by calling this real and this imaginary, and the whole thing is called the Argand plane, d at the end. Okay, so this is going to make a pi over 4 radians, and because this is 1, 1, this is going to be root 2, which is the modulus, which is r, which is the absolute value. Okay, I know a lot of information, but again, those are explained in detail. So from here, 1 plus I can be written as, by the way, I forgot to say, any complex number can be written like this in polar form. R is the modulus, theta is the argument or the angle. In this case, 1 plus I is root 2 multiplied by e to the power I times pi over 4. Looks like that's one of the solutions. Of course, you're allowed to add multiples of 2 pi to it to get infinitely many solutions. That's why this is multi-valued. So let's go ahead and take this and set it equal to that and see what happens from there, right? Because e to the iz, how can that equal to something like this? Well, the natural log is going to tell us the truth, right? If you natural log both sides, that's going to give us iz equals ln root 2 plus ln this, which is I times pi over 4. And finally, we're going to divide everything by pi, but I have a better idea. Instead of dividing by pi, why don't you multiply by negative I, because it does the same thing and it's easier. You don't have to deal with fractions because negative I squared is positive 1. Remember, I squared is negative 1. So this is going to give you the value of z, but you just have to distribute to negative I. Again, this is going to give you negative I squared, which is 1. So you're going to start with pi over 4 minus I times ln root 2. And if you write the square root of 2 as 2 to the power 1/2, you can bring the 1/2 over here and write the z as pi over 4 minus I times ln2 divided by 2, or however you're going to write the 1/2. So that seems to be a solution which we found by using the identity along with the Pythagorean identity. But isn't there another way to approach this problem? Absolutely. Let me go ahead and talk about that now, which we can call the second method, even though the first one we didn't call the first method. Hopefully you understand that. Now, we said that e to the iz is equal to cosine z plus I sine z. Now, here's the trick, and we use these tricks a lot. Replace z with negative z. That's going to give you e to the power negative iz. Now, cosine of a negative angle is going to be the same, but the sine of a negative z will be negative sine of z. So you kind of have to negate here because cosine is an even function, sine is an odd function. And hopefully you know what that means. Now, if you go ahead and add these two things, I sine z is going to cancel out, giving us a formula for cosine. 2 cosine z equals this. So if you divide their sum by 2, you get the formula for cosine of z, which is really cool because now by setting this equal to what we're given, you can directly solve the problem. So e to the iz will replace plus e to the negative iz divided by 2 will replace cosine. But in our problem, remember, we had 3 plus I over 4. Beautiful. Now, what are we going to do? Multiply both sides by 4. It's probably better. So we can have 2 here, and then this 4 is going to cancel out. And of course, we're going to have a 2 here, but that's okay. We can kind of write this as 2 times e to the iz plus 2 times e to the negative iz equals 3 plus I. Again, it's hard to see what z is going to be from here, so we kind of need to use substitution. Let's go ahead and call this w. 2w plus 2 over w equals 3 plus I, and then multiply everything by w. 2w squared plus 2 is equal to 6 plus 2i, and then we're going to go ahead and subtract. 2w squared is equal to 4 plus 2i, and then divide both sides by 2. W squared is going to be 2 plus I. So now we do need to find which number squared is equal to 2 plus I. Of course, there's a couple ways to do it. There's a formula. If you don't want to memorize it, I don't. You can go ahead and replace w with a plus bi. Yay, it's the name of this channel. And then square it and set it equal to 2 plus I. From here, you'll get a squared minus b squared plus 2abi equals 2 plus I. This gives you 2, this gives you 1, AB is 1/2, solve the system, so on and so forth. But again, this is a lot of work, isn't it? And after you find all of these, that's just going to give you W, and then W is e to the iz, so you have to do the natural log again, so on and so forth. But I think this is a better idea, even though there is a formula, and you can just use this method. Hopefully, you'll get the same answer. Let me know what you have. And this brings us to the end of this video. Thanks for watching. I hope you enjoyed it. Please let me know. Don't forget to comment, like, and subscribe. I'll see you next time with another video. Until then, be safe. Take care. Don't forget to check out Cyber Math and A+BI. And bye-bye.